high to low. And actually, if you imagine each molecule of a gas being a human, this is also how humans work. If there is a riot at the soccer game, most of you will run away from the riot to where there's less riot. A lot of collisions mean everything will leave from there and go to where things are more still and calm. Rule number 3. Because heat equals pressure and everything goes from high to low, you can basically just rearrange all of that to explain hot air rises. Hot air is high pressure air. And of course it's cooler above the source of heat, which is the surface of the earth. So it's hot here, cold there. Hot air is high pressure, wants to go where there's low pressure, thus cold air, so hot air rises, going from high to low.
Does that push cold air down?
Not yet, but we can imagine a scenario where that would happen, and I'll introduce that later. Finally, rule number 4 is about the behavior of that rising air. Remember I told you that water is special. As water rises, it gets further from the heat source and stops being a gas. It condenses, becomes a liquid, easier for gravity to get it, so it falls to the ground. As water vapor rises, it cools, condenses, and falls as rain. Those 4 rules are probably not new to you. The reason I've asked you to write them on your paper is those 4 rules underlie everything else that we will discuss about clouds and weather and rainfall and the trade current and Columbus. Before I move on to other lofty goals, can I clarify anything about rules number 1 through 4 that describe the action of our atmosphere?
Are you going to go over the diagram?
Yes, in due course. Nothing to say about 1 through 4?
Why does cold air sink?
Because it is still. And so, what would we say? Opposite of hot air rising goes from high to low, cold air. Oh no. Just because it's less not hot air. It's sort of the same thing as it being lower pressure, it's more dense insulation. Yeah, so it's easier for gravity to gravity. Yeah, easier for gravity to gravity. All right. Now I'd like to describe this thing. This curve up to here. This is a single convection cell. You can see that our planet has 6, and you can see that they wrap around the Earth sort of like an inflated life preserver for a child. If we cut a cross-section through one of those convection cells, I'd like to explain what's happening. And the tough thing is, none of this makes sense unless we get the whole thing spinning. So watch this. I'm going to start by describing air moving across the surface, but you won't understand what's happening there until I finish the cycle. So, air along the surface picks up heat and water because you know Earth is the heat source. Once we've turned on the sun, it is the energy source, light, absorbed, radiated as heat. Earth is the heat source. Agreed? So watch me. Because the Earth is radiating heat, air picks up that heat, and thus you get hot, wet air rising. hot, wet air rises. Now, because all that air has left, it leaves behind an absence of molecules, in other words, low pressure, where hot air is rising, that heat is driving the air upward, and it impacts into itself, creating high pressure. Being powered by the heat, you get a pileup of air in the colder part of the atmosphere where it cools and makes rain. Because this is where all the air is slamming into itself, you get high pressure. Now that it's cooled and dried, it wants to dissipate to an area of low pressure. There's low pressure there because cold air has fallen. The opposite of hot air rising. Where all the cold air is piling up on top of itself, you get a high pressure that wants to expand to the low pressure where there's an absence of air. There's an absence because heat has been added. So let me try this once again. It's not actually a square. It's technically just two arrows where hot air rises and cold air falls. This also gets a little bit displaced because of the high pressure, low pressure thing, where all the hot air is rising, it's expanding, pushing away into the low pressure because of the absence of air where cold air has fallen. Making a pileup, which is called high pressure, that spreads across the earth, picking up heat and water. Because it's hotter, it'll rise, leaving low pressure, which draws in more air to heat up and rise. Ruby?
Between the upper L and H, is dry.
Falling, dry, cool air. Dried and cooled.
Oh.
Yeah.
Is there one place where all the hot air goes up and then one side where it all comes down like that, or is it all just kind of going like that?
No, there are discrete zones on the Earth, and this explains the pattern of latitude biomes. So we'll get back to that. The funny thing about this is it explains almost everything you need to know about the Earth. Like, this will come up so much. I can answer the grasshopper effect, why we have deserts, why Columbus hit America, all sorts of stuff based on this.
That's supposed to be settle on the southern equator or on the southern hemisphere?
Because of where the arrows are, this could either be the equator, and this would be 30 degrees north, or this could be 60 degrees north, and this would be the North Pole.
And so,
Or they could be split that way.
The hot air is always traveling away from the equator, right?
No.
Looks
Let me do this, and then I'll answer that question anyway.
30 degrees north looks
When
like forward.
I'm not sure I can answer your question yet, but I will get to something that answers that question. So I promise I'll come back to that if not asking again. Anybody want to ask me anything about each individual cell? They're called convection cells because it's driven by high-low pressure.
Do they overlap with other cells?
Nope. And I want to make sure that I've clarified my explanation. Yeah.
Why does the dry and cold air fall from the low to high?
It's falling is what creates the low to high.
Okay.
So
So it just falls because of like gravity.
Right, because it's cold and dense, it's just falling. Because it's falling on top of itself and more falling on top of that, then you get like a pileup, that's what builds that pressure differential. Yeah.
Wait, so the pressure differential is built up from the falling air, not the heating of the air?
Actually, I'm sorry to confuse you, but it's both.
Yeah, okay.
Because don't forget, there is an input of energy coming from somewhere.
Yeah.
We're driving all of this by adding energy. So this energy is being transformed into this heat energy. Because of this heat, we power everything by rising hot air. So the one force which is being added to keep these changing If you turn off the sun, this all collapses.
Yeah.
So because of the input of energy, we have hot air rising. That leaves a low and creates a high. Because there's water in there, heat is dissipated to the atmosphere, right? Because of the condensation heat loss thing, you end up with cool, dry air, and then the pressure differential, high to low, dropping, building up the next high, which pushes to the low where the rising is left the absence. But it's all driven by the hot surface. I know that this can be really confusing, and I encourage you not to check out. Try to wake up. If there's a question, ask, because if not, you're going to be really confused for weeks here. Yeah.
Is there a difference between like currents created over like land and currents created over water?
Yeah, but the same principle applies on land and water. Those differentials are now about the percentage of water molecules as a function of atmosphere volume, and so now you got different relative viscosities and different heat capacities. So yeah, these are tweaked by the differential amounts of water vapor in the cells, but the cyclical pattern of one cell works on land and works on water. Yeah.
So obviously there's not just rain in those like couple of areas. So is this just like a general trend and there's also still smaller pieces of rain everywhere?
Yeah. This is the underlying first step in explaining global weather. Then there are a trillion things that also complicate conditions on the ground. And I'm not here to explain, the weather forecast in Australia next week, but I can tell you the general trends on Earth, and BT does. The wet-dry zones actually do line up cleanly with the biomes that we learned in UT3. What else? I really don't know how to teach this better, but I do know from experience over the years that a lot of you have questions, and I'd love it if you ask. Yeah.
I don't know if you're getting to this, but what does it say? It says temperate equals barrel.
Yeah, I'll get to that.
Oh, and why is your son angry?
My son's always angry. Yeah.
Would more heat in the earth during the process like with global warming stuff?
Funny thing about global warming is it'll change things about this. But that's not more heat hitting the Earth. That's technically more heat staying in the Earth. So technically, all of this just has more heat in the system, but the directions are still the same. If you've gone from 70 to 80, and from 30 to 40, and from 20 to 30, the heat is being added to all layers of this. So there's still the same rough differential between them, so you still have roughly the same forces. Climate change will really affect those details that Evan was asking about, but climate change won't stop the functionality of convection cells. What else? BT does. Climate change might change the elevation of the high-level winds. Yeah.
Are those like high level winds because like the jet stream stuff?
The jet stream is at this altitude, and also the grasshopper effect is this one. Anybody else? Okay. Now, this next thing is actually, this is going to be the worst explanation you've gotten all year. Our planet has 6 of these convection cells. They are continuous around the Earth. Technically, if you're into details, they're more like that. But if that's not easy for you, stick to this. Our planet has this miraculous distribution of gases in the atmosphere. So given the density of our atmosphere versus